Hey guys, today I'm going to show y'all how to do calculating empirical and molecular formulas in Texas. This is the TEAC 8C. If you're in my class, then by the time that we're going to do this, we've already calculated what's called molar mass and percent composition. If you don't remember what that is, percent composition is if you were to look at a formula such as C3H8 and you wanted to know how much of that compound is made up of carbon, you cannot just look at these little numbers, the subscripts, and tell me. You would think in this case that this compound is mainly made up of hydrogen, but you need to remember that percent composition tells how much a certain element in a compound is according to mass, not just the numbers. So in this case, the molar mass of this compound is 44. That's what I call the whole. The part of it that is carbon is this 36. So down here at the bottom, when you take the part divided by the whole times 100, it's actually about 82% carbon and the rest being made up of hydrogen. What we're going to do today is we're going to take those percentages, we're going to work backwards, and we're going to get formulas. So the first thing we need to lay down is what an empirical and molecular formula is. An empirical formula is the simplest, most reduced formula of a compound. As I put here, it shows the ratio of elements in a compound, but not necessarily actual numbers. I'll explain that in a second. So the molecular formula would be the actual numbers of atoms of each element in the compound. It would be some multiple of the empirical formula. In this case, CH2O, there's an understood 1 there and an understood 1 there. That is our empirical formula. If you were to work the percent composition of C6H12O6 and CH2O, you would get the same percent compositions. So the only difference between these two would be their molar masses. If they have the same percent composition, then we have to have a way to tell the two apart, and the molar mass is the way that we do that. Later when we work problems, that'll come into play. So if you have the percent compositions and you want to get the empirical formula, notice I didn't say molecular formula, but if you want the empirical formula, all you have to do is change your percent to mass, mass to mole, divide by small, multiply till whole. Now that's the jingle, but that doesn't necessarily tell you exactly what to do, so out next to it I put how you're going to do that. So what we're going to do is work a couple problems first, then you can work some on your own. The first problem that we have here is I want the empirical formula, so that's the simplest, most reduced formula for a compound that has these percents by mass of these certain elements. So the first thing you need to do is you need to come out to the side and organize your work. Go ahead and list your elements. So we have potassium, chromium, and oxygen. The first step is to change your percent to mass. Well, that's easy enough. We're just going to change the percentages to masses by changing the sign. So your chromium at 35.4% becomes 35.4 grams, and your oxygen 38.1 grams. That's easy enough. The second step is change these masses into moles. Well, the way that you're going to do that is you are going to take that number and you are going to divide by the molar mass of the element. I'm rounding from the periodic table. This 39.10 is the mass of potassium. So when you do that, you get a number. We'll use this here in a second. So chromium, I'm going to take my 35.4, I'm going to round his mass to 2 decimal places, and we get 0.6808. Now the one thing you need to consider when you're doing this is there would probably be more decimal places than just 1 up here. So this is not going to work out 100% exactly perfect, but it's close enough for what we need. So I've changed my percent to mass, my mass to moles. These number over here would be how many moles, and this looks kind of random, but if we go on with the next step, it'll make sense. The next step is divide by small. So you have these three numbers. You need to divide each one by the smallest of the three, and in this case it's 0.6803. So if you do that each time, then when you divide here you get 1, You divide here, you get roughly 1, and you divide here, you get 3.5. These numbers are what we need. These numbers tell us the number of each one of these elements in a compound, but we can't have K, Cr, O, 3.5. So the next step comes into play. We need to multiply until whole. So what you're going to do is you're going to multiply each one of these numbers by a number to make them whole numbers. In this case, 3.5 times 2 would be 7. 1 times 2 would be 2. 1 times 2 would be 2. If you have to multiply any of them by a whole number, then you have to multiply all of them. And now we get K2, Cr2, O7. Now here's our next problem. I've already worked it out for you. This is taking what we just did one step farther. In this problem, it's actually asking for the molecular formula and not the empirical formula. What we're going to do is follow the exact same steps, and I've already done it for you. I've separated it by these dashed lines. If you change these percentages to masses, then to change your mass into moles, you can just divide by the molar mass of the element. So I'm getting this, this, and this from the periodic table. It's the masses of these different elements rounded. Finally, when you have your amount of moles, you can divide by small, and you get 5, 3.5, and 1. Now we can't have the compounds C5, H, 3.5, and O1. Obviously we wouldn't write the 1, but we can't have that. So in this last step, I've already multiplied until whole. I had to multiply each one of these by 2, and you get the compound C10H7O2. Now that is an empirical formula. This is the lowest whole ratio of these numbers that I can get, but the problem asks for the molecular formula. So what I'm going to do is I'm going to clear our work really quick, and I'm going to show you how to do that. So if the molecular formula is some multiple of the empirical formula, it's going to have to give you a little bit more information. If you remember from earlier, the only difference between the two is their molar masses. So in this case, take the compound you get, C10H7O2, and go ahead and calculate its molar mass. List your elements, list the number of each from the formula over here, multiply by their molar masses on the periodic table. I'm going to round this to 12.01, 1.01, and 16. What we're trying to do is we're trying to figure out how much does your compound weigh. Then we can compare that to how much the problem is saying it should weigh. Your compound has a molar mass of 159.17. Sorry. Now what this is saying up here is that some multiple of your compound has a mass of 318. If you take the mass that it should be and divide by the mass of what you have, you end up with 1.99981, which we can round to 2. So what we need is we need some multiple of this compound that is 2 times heavier. All you have to do is multiply these subscripts by 2, and you get C20, H14, O4. This is your molecular compound. This is your empirical formula. So that's empirical and molecular formula. If you have any other questions, you can go ahead and email me.